In this next section, we are going to discuss how we interpret mass spectra for both elements and compounds. I'm also going to introduce some terms that you need to know with regard to interpretation of mass spectra. Okay, firstly, we are going to talk about mass spectra of elements. So what you're seeing on the screen now is the mass spectrum of chlorine. Okay, so firstly, you see two peaks at 35 and 37. So this tells us that chlorine has two isotopes, one of which is chlorine 35 and the second one is chlorine 37. Secondly, the peak for chlorine 35 is much taller than the peak for chlorine 37, and therefore we will call the peak for chlorine 35 as the base peak. The base peak in any mass spectrum is assigned a relative abundance of 100%. And any other peaks that are not the base peaks, their relative abundance is reported based on their intensities relative to the base peak. So what this means is that we notice that the peak for chlorine 37 has a relative abundance of 33%. So what this means is that for every 100 atoms of chlorine 35, we will find 33 atoms of chlorine 37. And this will help us calculate the AR of chlorine. So 100 atoms which are chlorine 35 plus 33 atoms which are chlorine 37 divided by the total number of atoms, which is 133, will give us the relative atomic mass of chlorine, which is 35.5 to 1 decimal place. Okay, so now we're going to move on to interpreting mass spectra of compounds. And obviously, because of the larger number of atoms present, the mass spectra for compounds will be more complicated. Okay, so what you're seeing on the screen is the mass spectrum for C6H5CONH2, which is an amide. This compound has a relative molecular mass of 121. So in this spectrum, first thing we see is that there is a peak that corresponds to the relative molecular mass at 121, and we will call this the molecular ion peak. Okay, so this molecular ion peak is formed when the beam of electrons strikes a molecule of C6H5CONH2. It removes an electron from the molecule, forming this cation radical. Okay, and then we also notice a very small peak at 122. When a peak appears at RMM plus 1. This is known as an M plus 1 peak, and for the purposes of H3 syllabus, we will assume that the M plus 1 peak appears due to the presence of carbon-13 that replaces one of the original carbon atoms in the molecule. Okay, next we notice peaks at 77 and 55. These are peaks formed when the molecular ion undergoes fragmentation. Fragmentation means that one or more of the bonds in the molecular ion are broken to give smaller cations, which can then be detected in the mass spectrometer.